It's a pleasure to introduce Roberto Laura, who is working with Marcelo Lozada, Leonardo Vanni, he comes to explain generalized context for quantum histories. Thank you.
Thank you. Well, the talk will be about a work we did in collaboration about quantum histories. The orthodox or the canonical histories are the generalized context, are the theory by Gell-Mann, Hartle, and Griffith, Omnes. And we did a small modification which we think that makes it easier to understand and solve some of the problems which appears in the theory of consistent histories. Well, let me start with a very brief introduction about classical histories. They are not really necessary for classical mechanics, but we can build classical histories and we can build probabilities corresponding to saying what is the probability that something is located in this region at time t1 and also is in this other region at time t2. State and properties in classical mechanics are, the states are represented by point in phase space, which is a space of positions and velocity, positions and momentums. And a property in classical mechanics is represented mathematically by a subset of the phase space. So we can make a partition of the phase space and consider the properties, just the properties which are generated by these atomic properties which correspond to the partition. We can represent them in a Hayes diagram where we pose the vacuum here, no property, with the property C1, the property C2, the property CT, C3, and then by making unions of these properties, we get the whole set of properties generated by this partition of the phase space. Well, I will omit the point of the lattices, and I will go back to the concept of lattice if I need it, because there is no enough time. But what is the lattice of properties in classical mechanics? Well, there is an implication, an order relation, which is given by the inclusion of the subsets of the subset representing the property P1 and the property P2 in the phase space. The conjunction of two properties is represented by the intersection of the corresponding subsets. And the disjunction is represented by the union of the subsets. The negation, the property of the negation of the property P is represented by the complement of the set Cp. With this structure, every partition that we can imagine in phase space generate a distributive and ortho-complemented lattice, which is very fine because we talk in this way. So when we name things, we talk using the structure of a distributive lattice. And the other interesting fact in classical mechanics is that the intersection of two partitions is again a partition. So it's a valid universe of discourse to talk in classical mechanics. What about dynamics? When the law of motions in classical mechanics is a map connecting points at time t1, the state at time t1 with the state at time t2. And the connection is given with an application S depending on the two times. And because we have this law of motion, we also can have the law of motion of the corresponding distribution of probability. I can represent the density of probability at the point x at time t by this function, and the density of probability corresponding to the point x at time t is connected with the density of probability at the previous time t0 in this way. So I have a kind of time transformation which is representing the time transformation of the law of motion of classical mechanics. How this goes when we compute probabilities? We can compute probabilities in this way. See, if I have a property P at time t, I integrate the density of probability in the corresponding set C sub P, and we get the probability of the property. This I may call the Schrödinger representation of the probability, of the computer of the probability, but we also have a Heisenberg representation. Just changing variables, I can represent the same probability only involving the density of probability at the previous time, t0, if I call Cp0 to the time transformation of the set Cp to the previous time, t0. So what is a history in classical mechanics? A history in classical mechanics can be obtained in this way. Just suppose I want to calculate, to compute the probability that P1 occurs in time t1 and P2 occurs in time t2. What I have to do is I have to take the set C2 corresponding to the time t2, I time translate this set to a time t0. I do the same with the set representing the property P1 at time t1. Then I make the intersection of C2, 0 and C1, 0, and I integrate in this region. If I want to have not the conjunction, but the disjunction, I have to integrate in the union of these two time-translated sets. Well, now, quantum histories. Well, it is not the, this is somehow obvious, so I will be very brief. We do not have subspace, we do not have subset, we have subspace in quantum mechanics, the subspace of the Hilbert space, and the property is represented by the subset of possible values of an observable, or by a subspace of the Hilbert space, or by a projector corresponding to this subspace. And the time evolution is given by Schrödinger equation. And again, we have the possibility of Schrödinger representation and Heisenberg representation. In fact, Schrödinger and Heisenberg name for the presentation are from quantum mechanics, not from classical mechanics. I just put this name to give the analogy. And we can have a Heisenberg and Schrödinger representation. The lattice of properties of quantum properties is a lattice where the order relation is again the inclusion, the conjunction is the intersection, but the disjunction is the sum of the subspace, which makes the whole problem of the whole difference with the classical logic, because now we have that properties form an orthocomplemented but non-distributive lattice, and the Born rule do not give well-defined probabilities in general. If we want to have a distributive lattice, and if we want to have the Born rule, because we want to compute probabilities, we can be checked in the laboratory, we have to restrict some way the possibility of properties, the set of properties. And the restriction is by means of a context. A context is a projective decomposition of the Hilbert space, which is given by some, I make a picture of a three-dimensional real Hilbert space just to fix the idea. We have projectors which have to be mutually orthogonal, and the sum of these projectors should give the identity, and in this way, we have a context of properties which are all the properties that can be represented by sums of this projector, or partial sums of this projector. If we do this, we have an orthocomplemented distributive lattice. The Born rule gives well-defined probability, and we can represent something like this in a very beautiful Hayes diagram. Well, the problem with the superposition of decomposition, the superposition of context. If we have this generator of a context C, and this other generator of another context C star, only if these projectors commute between themselves, if this is the case, then the operators obtained by multiplying a projector, a generator of this context by a generator of this other context, first, this product is a projector, they form a projective decomposition of H, and they generate a context which includes the context C and the context C star. I have to have this property in order to take two contexts and generate a more refined new context. Okay, how can we promote this for the case of histories in quantum history? Suppose I have a context of property that I call C1 at the time T1, and another context of properties that I call C2 at time T2. These pi1, k1, and pi2, k2 are the corresponding generators. And I have a time T0 where I know the state, the density matrix, the density operator. I would say that the context C1 and C2 are compatible between themselves if, when I translate these projectors to a common time T0, they commute. The translation is given by the, let me see where I have it. Well, the translation is given by multiplying by the time evolution and post-multiplying by the inverse of the time evolution. If this is the case, I will define the probability of the conjunction of the property P1 at time T2 and the property P2 at time T2 in this way, by the trace of the density operator at time T0 and the product of the two projectors, P1 and P2, translated to a common time T0. This is a generalization of the Heisenberg form of calculating probabilities, so that in this case I am involving two different times. It can be then different times. I put two just to give an example, more simple. If I want to compute the probability of the disjunction, I have to add the two projectors and subtract the common part, which is the product of the two projectors. This is our definition of histories, and one may ask the question, why should I learn this formal if Gelman and Hartel made another one which is well known? This was the question of one of the referees when we sent the paper. And fortunately, we found an answer to this question. Well, the first thing is, what happens if we apply our formalism to simple quantum cases? For example, to the quantum measurements. If we apply the formalism to quantum measurement, we have to consider, because one of the aims of the history theories is to eliminate the projection postulate and to consider the measurement as a quantum interaction between two quantum systems. So suppose I have a measurement where there is a system S and an apparatus A, where this state, this is the zero, the point of reference of the needle of the measurement instrument, and this is a some microscopic state, it evolves in time from T1 to T2 in such a way that the needle points to AJ. So this AJ of the instrument apparatus is connected, correlated with this microscopic variable at a previous time. Well, if we consider as a relevant variables, observable properties, this Qj and this Aj or Ai at the time T2, we found that these two contexts are compatible in our sense. They commute between themselves when we translate these two projectors to a common time. And then we can compute the probability that Qj have been at time, that we had Qj at the previous time T1 conditional to have the pointer of the instrument indicating Ai at the later time T2, of course this gives 1 or 0, depending on the case. So we reproduce in the logic of the conditional probability what we expect in a measurement. The other example is the double slit without measurement instrument. We are used to say that we cannot talk about through which hole pass the electron, which we have this, make a point here because we get in troubles. No? But the way we say in the formalism that we get in trouble is that if we consider these projectors at the time T1 and these other projectors on this region at time T2, and we translate this projector to a common time, we find that these projectors do not commute. So they are not compatible properties, so there is no way to build a language in which we can talk about these things. Of course, if we replace if we put here in the double slit experiment an instrument capable to detect through which hole the electron pass through the double slit, and here another instrument which is able to detect in which region it appears at a later time, and we do not talk about the position of the electron in a hole or the position of the electron here, and we talk about only about what the instrument registers, we have that these pointers positions at the time T1 are compatible with the possible position of this of the pointer position of the second instrument at a later time. The time difference between T1 and T2 is approximately the time corresponding to the flight of the electron from the double slit to this region of the space. And now it is possible to talk about what the measurement instrument gives. Of course, there is no interference because this is a difference. This is a different physical system from the previous one without measurement instruments. So we reproduce the common results. There is something about the idea of collapse of the state. Suppose we have a context of properties at time T1 and another context of properties at time T. There is more or less 20 minutes, or still? Okay, it's enough. Suppose I have a simple context, which is a property P1 and the negation of P1 at the time T1, and another context of just two properties at the time T2. And suppose these are the time translations of the corresponding projectors at the common time T0. And suppose also that these two contexts are compatible in the sense that when I time translate these projectors, this projector P10 and P20 commute between themselves, then we can compute, we are allowed to compute, because we have a quantum history where we can compute the probability to have P2 at time T2 conditional to have P1 at time T1. And the calculation is given by our rules. I have to compute the trace of I made it all in the Heisenberg representation at time T0. And the interesting point, this is all calculation, is that we have this expression. This expression gives a density operator rho star at time T1 evolving in time from the time T1 to the time T2, and then this evolved density operator is used to compute the probability of property P2. But this state, rho T1 star, is the time evolution of the state at time T0 to the time T1, here it is, and then it's appeared here the project. It's like the collapse, with the difference that we are not postulating the collapse, we are deducing the collapse in this calculation. If we agree that this is the way in which you compute conditional probability, this looks like the collapse. If we want to call it collapse, we call it collapse. This is a result that is, at least it is a result that Omnes also quoted in his book of quantum history. Well, but what happened? I guess I have a couple of minutes. What is the difference between our formalism and the theory of consistent histories? The theory of consistent history also considers a context at the time T1, another context at the time T2. In fact, we can have another context at the time T3, T4. Just everything I put in the history on 2 times to simplify the notation and to make more clear the discussion. The probabilities corresponding to the conjunction of the property P1, K1 at time T1 and P2, K2 at time T2 is given by this expression, which involves the state at time T0 and this product of projectors, which is called chain operators, which is put in this way here and in this way here. So this formula for the probability is different from the probability that we use. The other is that in order that this expression resembles what is the successive collapses of the state, because we measure at T1 and T2, but people who talk about consistent history do not talk about measurement, they talk about existence of things. But the expression is this one. And there have to be a consistency condition if we want this probability to satisfy the reasonable, the condition to be a probability. They have to sum 1. If we have a mutually exclusive event, the probability of the disjunction has to be the sum, etc. And for this to be true, they have to put a consistency condition. This consistency condition for us is very strange because the consistency condition involves the state at the initial time. We are accustomed to have a universe of discourse in quantum mechanics that we choose for some reason or for another reason, which is independent of the state. The state is something that which comes later to compute probability. But this, in some way, restrict the possibility of things about we talk to the characteristic of the state of the system. Well, what happened if we took the theory of consistent history with this thing that we don't like, but we put the consistency condition and we impose the consistency condition for all states, we obtain our formalism for generalized context. This is a fair result. So we can say that The problem with histories is the problem of the choice of a context of ordinary quantum mechanics multiplied for the number of times we have in the history. Because we can select a context at time t1, we can select another context at time t2. And so what is the context, the through context? If we have the problem of privilege in some context, in history, this is worse. But at least we can say, because of this result, that our possible families of quantum history are a smaller number than the families of history of consistent histories. And the other interesting result is that there is an old problem, which was discussed by Kent, that in the logic of consistent histories, it is possible to have a family where we can retrodict a property and another family of history where we can retrodict the contrary property. The defenders of the theory of consistent history say that this is not a problem because when we choose a context, we do not have to worry about the other context we do not choose. But anyway, this is a problem difficult to cope with. When in our formalism, this is not a problem. We do not have retrodiction or prediction of contrary properties. This is very briefly the result of that we think with our formalism. And the problem with our formalism is, in some way I said it, we do not have a single family of histories which is privileged by nature. We have to choose a family of history which is suitable for what we want to describe. If we want to choose a linear combination of position of a pointer in the measurement, we can. And we do not have an argument to people working, trying to do quantum cosmology are very worried about that because at the initial times, we do not have human beings who have to talk about something. They only have the universe, and we are not there. So this problem remains, but this is the state of our formalism. I mean, this is all I wanted to say.
Thank you. I think the problem you mentioned about the logic of the quantum histories is not a difficult problem. It's a very interesting one because you can have a history for a certain proposition and another history for the negation of the proposition, but you cannot be both. That is, the logic is not classical because the conjunct is not adjunctive.
Okay.
Yes, but it's easy to construct the logic satisfying the conditions of the consistent histories. It's a paraclassical logic. It's a kind of paraconsistent logic.
Thank you.
You anticipated already what I wanted to ask, namely the cosmological consideration. The formulation of quantum history I'm familiar with is the one of Gell-Mann Hartel. And there clearly the idea, I mean, that condition that may appear strange is still a condition on the wave function of the universe. That means not all universes are good for having the world that we see. So in the standard formulation, there is a desire of selecting a special history and having a theory which is not depending on measurement, on observers. It's just an history. For instance, Hartel made a proposal in which you just do positions, a history of position, and you get a formulation that is quite close to Bohmian mechanics. So but you already anticipated that. I mean, that people look at cosmological, so they don't want to leave free the choice of a family. They want to select one family.
Yes.
perhaps at the opposite extreme of that issue. I just, as a sort of a mathematical question, is it possible, say you're working in a finite dimensional system, is the set of possible consistent histories classifiable by some sort of equivalence, right? I mean, it seems like, say, I'm just working in a two-dimensional space. I should be able to find some sort of classification of possible, of the different possible structures of consistent histories. And then I go to 3 dimensions, right? It seems like that's an algebraically tractable problem. Is my intuition right, or is that not?
Well, I don't quite understand the question.
So I'm thinking about these contexts, right, as elements of an algebra, right? And so if I think about, what are the unitarily inequivalent representations of an algebra on a finite dimensional Hilbert space, I think that's...
You mean which are a way of classifying all the possible set of families of quantum histories,
right, of contexts,
which form a context between themselves.
Right.
I didn't try it. I don't know.
Is that hard?
I just use.
Right. Yeah. Right. Oh, yeah. Absolutely. Right. But it still seems like if you have a finite dimension. I mean, again, I'm always just sort of interested in seeing what things can be enumerated, and so I was just wondering whether that's an enumerable problem.
We just try to deal with interesting for us
right.
possible families. Describe a measurement, the carbon double slit experiment. We do not get involved in the classification of all the possibilities.
Right, because you'd like to. I would like to find
because
the simplest system I could see the effect in, right? Right, and so some finite dimensional system where you could see the most unlikely or the most surprising physical effect.
Other question?
I'm somewhat familiar with the Griffiths, the basic consistent histories formulation, and I'm just trying to get a handle on my understanding, my impression from the program is that the quantum state then becomes kind of an epistemic object. In other words, the ontology, I'm trying to get a handle on what the ontology would be, and it seems as though the consistent histories program needs to, or kind of assumes that the world is the way it is, and that then the quantum state is just going to be a measure of our ignorance over what actually obtains in the universe. So I just wanted to clarify if that's correct.
Yes.
Okay.
Yes.
Take it to here.
Excuse me for I never been able to understand this approach, consistent histories, the coherent histories, all these histories. And for example, now you say that they have contrary properties and you do not have contrary properties. So what? Well, what is this approach supposed to do? Because you mentioned that they don't want measurement. If you want to do measurement, then we know how to calculate them. If you don't do measurement, what it's good for? What it means? What probability of what? I ask every person related to consistent history. Probability of what? And I never got an answer. You have an answer? What? Well, it was? No, what's possible?
According to German, there are various schools, but according to them, they want to select the two histories of values of some associated to operators, but they don't think of operators as being related to measurements. They think that the values of operator are real, and you have to create, our world is a succession of values of certain operators.
A measurement is a special quantum interaction between two systems. System which is the observed system, and the other system which is a measurement instrument. But both are described by quantum mechanics. Or that is the aim of the whole project of quantum physics.
What is the aim? Again?
The aim of the project is to consider the measurement as another quantum process and not to privilege the measurement instrument.
Every interpretation tries to do this, unless it puts measurement as a primitive. But it's still. They talk
Just a
about
second.
this families, whatever. What is? I
Yeah.
never understood what it might mean.
I mean,
asked probability of is it really happened, not happened? I go to laboratory, I start with electron and go particular beam splitters, whatever. So, and then what this formalism, big formalism, they spent, many PhD students come out, they calculate all these decoherent functionals, what they mean.
But no, what they mean is not so obscure, Lev. They want to have, they have beables, I mean, whatever, which are obtained by a succession of operators. They want to say that is a possible history of a universe. Now, that program is not finished yet. Okay? That means they didn't achieve yet a complete goal of selecting one family. But what they have in mind is not so obscure.
I would like to add something because I know this project, Roberto's project. The difference between the traditional histories program and what they are proposing is that they pretend to solve the measurement problem and they intend to be a full interpretation of quantum mechanics. Here, I think that the proposal is more humble in certain sense. They are giving a formalism, and this formalism perhaps has to be.
Perhaps it
Yes.
can include a more strong postulate arguing that such family history is privileged or are they unique that, but it is. But I wanted to say something. I don't know how I can compute in ordinary quantum mechanics the probability that in the double slit experiment, the probability that at time t1 the electron is found at this hole and time t2 it is found in this point of the, if I do not use histories. Unless
Aaron of Berger-Leibovich, 1964. They exactly said, make measurement here, here, and here. What is the probability that you'll get this set of outcomes? Has been done by Aronov in 1964.
No, before Wigner before, because it is called Wigner formula, and that is the formula for the succession of measurement. That was used by Aronov.
Sorry,
Was Wigner before?
I don't.
No,
Tell me, show me. I don't know.
just a remark about Lev's question. They are speaking about contrary properties and not about contradictory properties. This is a big difference. Yeah.
No, but my question is it good, is it bad, so what? If this doesn't have any physical meaning, we can have this property. In this family, for example, now, Griffiths wrote a paper against me, and he said, that according to this family, it's this, according to this family, it's this. So,
No,
forget
Griffith. Griffith is obscure.
Gelman gave me 40 minutes lecture. He remembered his book, his book word by word. But you ask him question, he just continued to read his book without having.
So, just, if I could just, this should wrap it up. This should wrap it up easily.
Long session of discussion, so we can continue to discuss.
So yeah, I understand Lev wants a dynamical wave function, and he wants it to be ontological, and so do I. So that's his concern. And in this program, the wave function is just a measure of our ignorance. The way it solves the measurement problem is it says the universe is just everything that happens. and they posit implicitly that everything happens. All events are there. And then the wave function is relegated to simply a description of what we didn't know about. And I think you don't like that, and a lot of people don't like that. But it's just, that's the program, and it's one way you could do it.